All right, I will begin with a word of prayer. So, Heavenly Father, we thank you for this week, almost completed. We thank you for the weekend about to start. I just pray you be with us today, help us to understand a little bit more about topology and how it all works. So, in your name I pray. Amen. So, we tried to go on without paying our dues last time, which is a bad move. There's some elementary notions that we need to stop and dwell on. Otherwise, for example, the theorem we tried to understand last time won't make a bit of sense. So, some of the things we're trying to understand this meeting, basically we're in section, mostly trying to wrap up chapter 3 of Manifold. And how was that? What did you think of it, Daniel?
Oh, it was the best chapter I've ever read. It's actually
everything you've read was really
everything
interesting.
I read was the best book I've ever read. It's actually at the post office.
It's at the post office
I got
now?
the email this morning.
So you can get it today?
Maybe, I don't know.
Okay.
Today or I think it's open tomorrow.
So if you want to, you can borrow mine for the weekend, because just in case you can't get yours.
Okay.
I want to make sure you have it to read. Okay, getting back to the chapter. So basically, there's some ideas missing, right? Like we talked about continuity of a function, right? But if you think back to Calculus 1, what did I do? I mean, we start by talking about a limit, right? If I was very, very adventurous, I might have talked about a limit point in Calculus 1. I don't remember. But then we build our way to this notion of a limit at a point. We say a function's continuous at a point if the limit of the function is the value of the function at the limit point. And then if that's true for all points in a set, then we said it was continuous. Well, this is kind of upside down, right? We've defined continuity of a function in terms of it being, the inverse image of an open set being open once more. But if you ask the question, what does continuity at a point mean? We don't know. So that's one of the things we want to get to, is like recovering some of those ideas, like continuity at a point in terms of sets. There's no limit here. So that's the interesting thing, is we're talking about continuity and all these things, but there's not a limit to be seen. So, definition. And this is exposited really beautifully in chapter 1 of this book, this notion of an adherent point. But here it is. So given to be a subset of a topological space X, X is again a topological space, one writes, so here's the mysterious bar, B bar, not to be confused with B bar, for the intersection, and here it is, B bar, is the intersection, we'll use this as a builder, intersection notation, intersection of C, such that what? Such that V is a subset of C, is a subset of X. And what kind of C is that? C closed. So it's the intersection of all closed sets which contain B. So this is also called the closure of B. All the points in B bar are said to be adherent to B. So this is also known as the closure of B. X, an element of B bar, is adherent. I forgot how to spell that. Sad but true. Yeah. If Michael was here, he could tell me some kind of rhyme so that I wouldn't have had to look in there. Adherent to B. See, Michael, we miss you. Adherent to B. I think it's fun to just stop and take a second to draw a picture of this. I'll do a two-dimensional example. So here's a set which is neither open nor closed, right? It's neither open nor closed in the plane in the Euclidean topology, right? And if you start thinking about closed sets which contain that, there's all kinds of them, right? Here's one. Right, there's a closed set that contains that. I'm in every one of these, I mean it to be shaded, all right? This is also shaded. Stupid whiteboard. I'm also including all the points inside there, right? let it be under, I don't know how to, stupid pictures. Wish I could shade. Oh well, maybe 20 years from now I'll have some kind of virtual board and I'll just be like, Phil, click, ha. No, I'd never get it working. All right, and then you got this one, right? And then you got this one, right? And so forth and so on. And you can just look at, and of course they don't have to be like that, right? There could be another one that's like this, whatever, right? There's another one that's like this, and you just, I mean, the intersection of all of these, though, it closes down on B, right? And what it eventually does is it fills in those dots as well, right? And that's the closure of B. And so you notice that there are certain points, like this one, so X is not an element of B, right? But X is an element
B bar.
of B bar. So X is adherent to B, even though it's not in B, technically. Okay, so that's the notion of a closure and an adherent point. Let's see here. Some generic comments we can make about this. So this example 3.13. Sorry, I'd be very boring. I'm more or less reading from Manetti, but you know he's really on point here and nice, worth reading. So A subset of B. If A is a subset of B, any closed set containing B also contains A. Any closed set C which contains B also contains A, right? And so if you think about that, that implies that what? The closure of A is what? A subset of the closure of B. Right? And he says, likewise, if you think about families of sets, right? If you have a family of subsets of a topological space, the union of the closure is a subset of the closure of the union. And his notation makes me think countable union, but maybe he doesn't mean that. You know, does this mean arbitrary union? Or just countable union? What do you guys think? We also have that the closure of any particular thing in the union, right, is a subset of the closure of the total union. Hot. Should get some more LED lights. Actually, those lights are LEDs, but they're disappointingly, they're still pretty hot. The ones in the colored thing. The ones I have at home that are cheaper don't make as much heat. I kind of doubt the wattage rating on those. I bet they're higher than they say. Anyway, I digress. If you pick a point in here, can you show it in here? What would it mean for X to be an element of this? And let's try to do it. Let's try to do it for alpha and an index set. Okay. Not necessarily. It could be a real. Could be the reals. Could be whatever. Doesn't just have to have cardinality. Alpha not. So then what? This is, that implies that X is an element of the closure, right? Of
At least.
right I guess I'll say alpha for some alpha, right? But that means what? That means that X is an element of C for each C which contains A alpha, right? What does it take for something to be in this set?
X is an element of C for each C containing the union of all.
Yeah, so let me do it over here. So X has to, you said X has to be, let me say Y. Y is an element, I don't want to, so Y is an element of C for each closed set C which contains
The
union of AI, or I say A alpha over alpha lambda, right? I'm trying to bump it up to that. Or maybe not. Maybe that's what he means already by this notation. I haven't digested Minetti finely enough to be sure of that or not. So.
Well, each C containing alpha, or each C containing the union automatically contains A alpha.
Sell it to me again.
Sorry, no, I'm trying to think, like,
Again, upstairs in my box. But oh yeah, you need to put it upstairs in the mailbox because the grader will go pick it up there. Yeah.
Okay.
Math department,
Okay.
my mailbox. Okay. You go guys go this way through that hallway and then up the stairs is the fastest way. Okay. I don't have people come to my office. Calculus 2. Rarely from other classes, but physics. Physics is a continual annoyance. Its very nature is annoying. I'm sorry. I actually like physics. I digress. Okay, so where are we? You're here.
so what I'm thinking is that if X is in each C, or is in C for each C containing A alpha, then it must be also be in all the C's containing the union of them all. I'm trying to think of like how to phrase that.
I mean, it is of course. I mean, maybe I know that this. Now I've dug ourselves. So I should say like alpha naught or something stupid,
Yeah.
so I can tell. So of course this contains.
Yeah, alpha naught.
I mean that we know. Every set in the union is a subset of the union.
Mm-hmm.
I see it.
Can we use what we had before, like the first part of the example?
Oh, the closure of A is a subset of the closure of B?
Yeah. Because since A alpha naught is a subset of the union of all of them, then the closure is going to be,
Oh, okay.
yeah.
Yeah. That's a better way. Let's be more pointless.
Is that a pun?
Was that an intentional reference?
Huh? Yeah, I mean, let's give a pointless argument. So we have we have AJ is a subset of the union over I, AI, whether this is a countable or uncountable union. And that implies what? The closure is a subset of the closure of the union. Right. Yeah, that's better. Thank you, Jamie. By this. Yeah, I mean it's a pun, but it's a meaningful pun. All right. Let me go on. All right, so there it is. Finally got through that. Now, so I'm about to subject you to a barrage of definitions. So I'll write them over here, I guess. No, I guess I'm going to erase that blue. Maybe I'll get a chalkboard in here. Wouldn't that be nice? Yeah. Should get a chalkboard.
Breathing in chalk dust.
Yeah, get a little
I
dusty.
prefer chalk dust to this stuff. And shading. And math culture. Proper math culture. All right, anyway. Definition. A subset is dense. What's it mean for it to be dense if closure of A is X? He says equivalently, if A meets every non-empty open set of X. More generally, if A is a subset of B, and A and B are subsets, then A is dense in B when B is a subset of a closure. If you write that down, that's kind of another definition. If A is a subset of B, these are subsets of X, I suppose. It's inside some topological context, right? Then A dense in B, how is that defined? When B is a subset of the closure of A. All right. So here's some examples he throws out. He says in a space with the discrete topology, no proper subset is dense. Right? So what was in the discrete topology? What were the open and closed set? What set was closed in the discrete? Oh, I'm sorry, I'm thinking, what was the discrete topology? I forgot already.
All possible subsets are going to be open sets.
Right, so X paired with the power set of X is the discrete, I mean, this is the discrete topology, right, for X. So, what he just told me says, in a space with the discrete topology, no proper subset is dense. So let A be a subset of X, right? And A not equal to X, right? A not equal to the empty set, I think. Proper subset. So what closed sets contain A? What's closed?
Wouldn't everything be closed? Because you can just look at the complement of whatever set you're looking at. That's going to be a subset, therefore the original
Yeah,
set is going to be closed, right?
I think that's exactly right. If U is a subset of X, then X minus U is also a subset of X. And hence, X minus U is in the power set, right? AKA the topology here.
That means the U is closed, which means the closure of U is just U, which is
So what's
the
the
proper subset of X.
So what's the closure of A?
It's just going to be A.
That's what I think, yeah. Oh, okay, that's the point. So the closure of A duh, is equal to A, which is not equal to X. Okay, so they were done. Sorry, I lose these things that have no particular geometric meaning to me. I lose track of what we're doing mid-example. It's just, it's my naive upbringing. All right. A more interesting example, the set of rationals, all right, is dense in the space of the reals equipped with Euclidean topology. Here's an example we haven't done yet, and I don't intend to do at the moment. Example 4, he says, in a space with a cofinite topology, any infinite subset is dense. We haven't talked about the cofinite topology yet here. I'm saving it for another day. It'll take me some time and energy to talk about it. We'll get back to it though. I don't know, in the research last semester, there's some theorems about density which are interesting. Sometimes, like I guess a standard proof technique in advanced mathematics, if you can prove something for a dense subset of some space, a lot of times there's a theorem that says it extends to the whole space. So like one of the ways of attacking limits, I mean, at the start of our research, when we were trying to study difference quotients over algebras, the trouble with these algebras that are, not complex or not quaternions or not the reals is that they're zero divisors. They're a times b such that ab is equal to 0, yet neither a nor b is 0. So if you try to take the limit over like all points near some point, and you're dividing by these quantities which are, you're trying to divide by quantities, well, some of those are zero divisors and you just can't divide. So like, how do you deal with that? So the way we dealt with it originally was just to not use difference quotients. But more recently I found papers which in fact use something called a deleted limit. And they use a density argument. Because, what is it, I'm trying to remember which is dense. Is it the bad ones or the good ones?
The good one.
The good ones are dense, yeah. So the set with the set of units in these algebras is dense, because the zero divisors are always some kind of like lower dimensional piece of it, like just a line or just a plane. So there's always many points near that bad point, which are units, which are multiplicatively invertible. Anyway, so we needed that idea of dense there, and this is one of the things I'd like to understand a lot better than I do at the moment. But anyway, there's the definition. A is dense, the closure of A is X, like that. Okay. Are we good? Yeah, let's see, so next definition, try to get through these without too much time. Interior of B. What's the interior? The interior of B is B upper knot. All right, and that's a subset of B. It's a subset of B in X. All right. I guess I don't mean to. Don't read too much into these. I'm not, don't read too much into those. Okay. What is it? It's the union of all open sets contained in B. All right, this is the interior of B. Equivalently, the interior of B is the largest open set contained in B. The points in the interior of B are called?
Interior point.
Indeed. X is an interior point. All right. Again, we could draw a picture similar to the one I just drew. It might be fun. I don't know. So if this is my set, think about interior, you think about open sets inside this. You see what's going to happen. You'll get those points even. You never pick up these points, right? So it's essentially, the interior of this is going to be the same set, but then with a fuzzy edge where it was filled in. So the interior is an open set. Well,
So it's just the complete opposite of B bar.
yeah, I guess I haven't proved to you that the closure is a closed set yet either, but it is. So that, I mean, that's where we're going there. All right.
Are we then gonna do like a B bar B degree is just B, like prove those sort of things, or?
We're getting to some results like that. Let's see what we got. Here's the next thing he says is a subset of B of the topological space is open if and only if B is equal to the interior of B, and it's closed if and only if B is equal to B bar. So I guess that's a little proposition. He hasn't even had a proof, so I think it's a little more than just parsing through the definitions. Let's think through it. So B equals to B naught if and only if B is open, and B is equal to the closure of B if and only if B is closed. So actually both of these arrows are pretty, I mean, if B is open, right? Then B is an allowed thing in the union, and there's nothing bigger.
Also B, yeah.
I mean, you can't have a set that's larger than that, which also contains B.
Mhm.
That's impossible. So I mean, that is the largest.
Right.
Go in this direction. They go in that direction.
B naught, or B, the interior is going to be open since it's a union of open sets.
Right.
So B is open.
Right. If this is equal, and that's a arbitrary union of open sets, it's open. So, right. Down here, let's go this. Well, I know which direction you guys want to go first. Forward. Let's go this way. What's that? This way. Okay. So suppose B is equal to the closure of B.
Well, the closure of B is an arbitrary intersection of closed sets, so it's closed.
Do we know the arbitrary intersection of closed sets is closed?
I thought we did.
No, it's just finite and ending.
I thought there was finitely many unions in there, like arbitrarily intersections. I don't know.
I thought we already knew that.
I think you're right. I think he's right, actually. We don't know that the, we know arbitrary unions of open sets are open. We know finite intersections of open set are
And
open.
it's switched for closed.
Yeah, it's the other way around. We know finite unions of closed sets are closed. We know arbitrary intersections
Right.
of closed sets are closed. No, I think,
Oh,
yeah.
yeah. So actually, what you did for the first one then, because you used arbitrary unions, that wasn't valid.
No, that was
No,
okay
it's
because
okay.
that's an open. This is open. This is closed. It's different.
Oh, okay.
See, that's the thing.
Oh, okay, that makes sense.
Right. I mean, they're different. It's a different world.
What?
No, no, I can't see it. Okay, so nothing important. Something political. It's okay. So, right. So if B is equal to B, so this is again a closed set. So if this is equal, then B is closed, because the arbitrary intersection of closed sets is once more again closed. Okay. Conversely, if B is closed, it's one of the closed sets which contains B.
Mm-hmm. And it's the smallest.
And it's just, yeah, it is the smallest one that contains B, so there it is. Okay. And then at this point, he mentions a variety of things I can't write because I'm not French. I will write them in a boring, less French notation. For example, the closure of this guy is this guy. And that's also the closure of the opposed set, or the closure of the Kloppen set. I'm not sure if that's entirely a joke. I've read it in a book somewhere. And then, of course, the interior, right, is this, and similar comments apply to this and that. So, and of course here I'm talking about with respect to the what? With respect to the Euclidean topology. Yeah. All right, moving along here. What's the boundary?
The closure with the interior removed.
That seems right. Now he uses a notation I wouldn't usually use here. The boundary, and because what he's defining is the topological boundary. And so he says the topological boundary, I mean this is his notation, so I guess I'm stuck with it. He says partial B is closure of B minus the interior of B. You know, remove the interior, like Nathan was saying. And he says you could also look at it as the closure of B intersected with the complement of X by B, which also makes a lot of sense. What are boundary points?
Points in the boundary.
Right, so X an element of partial B implies X is a boundary point. I will sometimes, if I'm in like a manifold class or something where I care and where it might be an issue, you might want to distinguish between the manifold boundary and the topological. A manifold with boundary, there are a certain subsets of charts which are like smooth maps to a half space, and then other ones might be like maps to the whole space. So part of a manifold boundary is diffeomorphic to, like I said, a half space. So there's like some edge to it, and that's the topological. That's the boundary of the manifold. That edge to the manifold is actually a subset of the manifold. In contrast here, this notion of boundary doesn't have to be in B. Like, so I sometimes would call this boundary of B, and then I would use partial B for the manifold boundary, but it won't be an issue in here because we're not doing manifolds. I'm just saying there is a distinction. So if I was to use this notation, the boundary, as in topological boundary of the open set A to B, would be the two-point set AB. But the topological boundary, the manifold boundary of the open set A to B, well, the open set A to B is a manifold without boundary, so this would be empty. And so there is a distinction between these terms. Not usually an issue. It's just something there to be aware of. Okay. Anyway, that said, for us, boundary of B is going to be topological boundary. Okay. What can we say about the boundary points in terms of what they're adherent to? What points are the boundary points adherent to?
B set itself.
Yeah, they're adherent to B.
And X minus B.
Right, they're adherent to both. So that means it's adherent to and X minus B, right? You can see that here, right? It's an element of the closure of B and the closure of the complement to B. It's on the edge. Of course, that means boundary point. Okay. Whatever that means. We're defining what that means in terms of set theory. That's the interesting thing, right? All right. Now we come to the definition of a neighborhood. You want to be my neighbor? Let's see here. You guys didn't watch Mr. Rogers' Neighborhood, did you?
I used to.
You used to?
Yeah, when I was little.
It's still relevant?
Yeah.
It's a
I still
long
see
time
things
ago.
on Facebook all the
Yeah.
time. Okay.
Yeah, okay, good. Let's see here, X, topological space. I like the neighborhood of make-believe. That was really what I was living for. I didn't really care. And once that train came out, I was like, yes, finally the good part. And it always was too short. And you always come back to that other boring place. Start putting on shoes. And who cares about shoes? Putting shoes on. Who wants to see put on shoes? Boring. All right, anyway, sorry. X, topological space, and X a point. A subset U of X. Okay. X has always been a topological space, and right, I'm just not going to write it. I'm going to get tired of it. About the 14th time I write topological space, my hand's going to cramp into a gnarled. All right, so U, a subset of X, all right, is called a neighborhood, which I will abbreviate by neighborhood. A neighborhood of X, if what? If there exists an open set V, right? If there's an open set in the topology, such that what?
X is an element of V,
Right, X is contained in V,
which is a subset of U.
and V, right, V is a subset of U. In other words, X is an interior point of U. Because it's contained in one open set, which is contained in U. That makes it an interior point, right? To draw a picture of this, I think it's useful. Neighborhoods don't have to be open themselves, right? Neighborhoods could be like that, around some point X, right? It doesn't, I mean, it could be half open, it could be one of these kind of deals too. I mean, who knows? The concept of a neighborhood is very greedy. But the point is, inside there, yeah, there's some V, which is open. Right? So, of course that makes X an interior point of view. Right? And now he starts to play games with the family of neighborhoods of X. So we use this, try to follow his notation. Funny looking eye of X is the family of neighborhoods of X. Family of neighborhoods of X. Right. He says, by definition, if A is a subset in a topological space, right, then the interior of A is what? He's going to use this, kind of showcase this notation with this. So A is a subset of the topological space. Then the interior of A we can write in terms of this family of neighborhoods how? It says, in particular, a subset is open if and only if it is a neighborhood of each of its points. Does this make sense? So A is a what? A is a neighborhood of X. What's that mean?
Means there's some open set contained in A that X in.
Right. Which says that X is in the interior.
I'm not sure I really understand the set X an element of A such that A is an element of the interior.
Well,
Is A
this is A is, that means A is a neighborhood of X.
right?
Let's just think through it again. I mean, if X is an element of A, where A is a neighborhood of X, this means that there exists an open set around X
Okay.
contained in A,
Okay, yeah, got it.
which then means that, you know, that's part of the interior. It is awkward to me to start with, I don't know, but there it is, okay. Now, there's a lemma 3.2, all right? And I'm just gonna, I think I'm gonna read through the rest of this section. I think I've written enough for this section, I'm gonna go on. But I'm gonna read the rest of the results here in section 3.2. The family of neighborhoods of a point is closed under extension and finite intersection. I said I wasn't gonna write. I'm not gonna prove though. So it's lemma 3.20. It's like if U is an element of the neighborhoods of X, right? And U is a subset of V, then V is an element of the neighborhoods of X. So like a picture of that would be something like, it's just what he says, it's like extension, right? What that's saying is that if this green thing is a neighborhood,
Then you could draw anything.
then so is this.
Makes sense.
Because if the green thing's a neighborhood of X, then certainly the red thing is also a neighborhood of X, because the green thing already contained within it the open set which contains X. The other, I thought I wasn't going to prove that. I'm sorry. If U and V are elements of the neighborhoods of X, then the intersection of U and V is, you guessed it, in the neighborhood, is a neighborhood of X. That also makes sense because, why? These are actually kind of fun to prove. Like, yeah, I'm sorry, I should. So if that's a neighborhood, right? If the green thing's a neighborhood, right, of X, and if I was to take another neighborhood of X, say like this one, then okay, well there's a different, there's a different. Let me make it more interesting. There. That's a neighborhood inside the red set, which contains X. So how do you get a neighborhood inside the intersection, which contains X?
Take the intersection.
How do I know that the intersection of those dotted black circles is again open?
It's in topology.
It's in topology, right? Because we assume such. All right, so there you go. So that then shows that the intersection is also a neighborhood, because in the intersection there is also contained an open set which contains X. Lemma 3.21. Let B be a subset of a topological space X. A point X belongs to the closure of B if and only if the intersection of U and B is non-empty for every neighborhood U.
can I ask a quick question?
Yeah, please do.
This was, like the previous part right there, the definition, and then like where you used subbuilder for defining the interior of A.
Mm-hmm.
The part of that that makes sure is still an open set is the fact that V is like the neighbor, like it's an element of the topology. That's what makes sure that that's still an open set, correct?
For something to be...
As far as neighborhoods go.
Well, I mean, the question is what's the interior, right?
Yeah.
The interior set of points inside A, right?
Mm-hmm.
For which there's something in the topology, some open set in the topology, right?
Mm-hmm.
Which contain X and are subsets of A. But that's the same thing as saying that X is an element of A, where A is a neighbor in this neighborhood of this local neighborhood of X, because to say A is in here means that there's an open set around X, which is also contained in A.
Okay.
It's the same thing, it's just written in a
Okay.
convoluted way. That's not too convoluted, I suppose.
Makes a little more sense now. Okay, sorry.
I'll tell you what, it makes more sense me saying it to you than it did when I read it earlier today. I'll tell you that. Which didn't say much. I'm kind of dense. Not in the technical sense, though.
Can't be too sure.
I'm a dense subset of what? Sorry. Stupid. Lemma
Math jokes.
3.21. Let B... There is no more pure joy than insulting someone with mathematical terminology they don't understand. You know, it is a joy. Let B be a subset of a topological space X. Then X is an element of B bar. Well, excuse me, I don't know how to say this. It's kind of stated weird. X, an element of the topological space, belongs, I don't know why I'm going to write it as he writes it, just belongs to B bar. Why doesn't he just say X is an element of B bar? Maybe it's so that the typesetting's better, I don't know. If and only if. Sometimes when I have unnecessary words in my notes, it's just to make an equation go somewhere I want it to. If and only if U intersect B is not equal to the empty set for every neighborhood U of X. In some sense, writing neighborhood is redundant. You could cross this neighborhood out and not lose anything. You could say for every U that's a neighborhood of X, because I of X is the neighborhoods of X. I don't like the way that reads. For every neighborhood U, element of the neighborhoods of X. Like, why don't I just say for every neighborhood of X and just write U element of X to mean that? Potato, potato. I don't know, whatever. Can we draw a picture? Does this make sense to you guys intuitively?
And that's sort of like how we defined. Well, I feel like this is similar to how we actually defined the closure in advanced calc.
Oh.
Or at least the boundary, it was similar to this.
Yeah, let's say I usually define boundary in advanced calc to mean that there's some points inside and some points outside, right?
Yeah.
So that's an interesting point is like this one, right? X belongs to the closure of B if and only if, so we take any neighborhood of X, which could be something, I guess the difference is neighborhood here doesn't, I mean I use open sets in advanced calc. Here neighborhood is, you know, whatever. But the point is the intersection of this neighborhood, right, and B is non-trivial no matter which one you pick. Any neighborhood of X non-trivially intersects B if X is in the closure of B. Okay, well that I mean geometrically that's not a surprising theorem. But of course, the proof is again set theory. If finally, one more definition. I'll leave the proof of that one to you guys. Definition. If we have X a point in a topological space, and if we have J a subfamily of the neighborhoods of X, right? Then this J is a local basis. It's a local basis of neighborhoods at or around X if what? What do we need? For any U in any neighborhood of X, U, there exists what? There exists A in J such that what?
Did we define local basis before?
No, we defined topological basis. It was a collection of subsets of the space whose union covers the whole space, and there's one more condition.
Oh, I'm sorry. I thought we were proving a lemma. I can't read. That's why I was confused.
No, it's useful that you asked that, though. It's called the basis of the topology if every open set in the topology can be written as a union of elements in the basis. A subfamily of the topology is called the basis. And then we had a theorem which I'm remembering the theorem, not the definition. And the theorem said that you have a basis for the topology if it's a subfamily of the power set of the set, and the theorem said that there exists a topology on X for which a given subfamily of the power set is a basis if the union over the basis covers the whole set, and if for any pair in the basis, any point in the intersection of two things in the basis is once more contained by something else in the basis. This is theorem 3.7. And I do think that the word local basis is not, I think it's being used in somewhat the same sense. Let's see here. But we're making a definition. So, more a question of style than requisite logic. Okay, so then what? Where was I? Oh, we're missing a condition. A is what? A? What? Oh, A, yeah. What does A have to do? A has to be a subset of U.
Okay.
For example, in my examples, in the plane here, a local basis at a point would be given by, like, I guess it depends on well, is I of X is the family of all neighborhoods? Or is it a particular family of neighborhoods? I think it's the family of all neighborhoods of X, right? Otherwise, well, I'm assuming I of X is the family of all neighborhoods. If it's family of all neighborhoods, then certainly I could use like open disks, right? Or I could use open diamonds. or all kinds of stuff, really. Right. So like your epsilon balls with respect to the different metrics induced from different norms at a specific point would give you like a local basis at x, for example. All right.
And a local basis could be just a regular basis. Well, I don't know.
A regular
Seems like it could, but not necessarily, I guess.
I don't think that'd be the case if it's disconnected.
Yeah, that's what I'm
for
thinking.
example.
That's what would be local.
let's see here, it says let U be a given neighborhood. All neighborhoods of x contained in U form a local basis at x. So you could throw out you could throw out some of the stuff that's too big and just like the local basis could be it could be closer to x, right? A local basis. Local basis. Local basis. No, it makes sense. Sorry. I wasn't trying to be derisive. It just comes out that way sometimes. Maybe that's why I like Cruz. If beta is a basis for the topology, open sets in B containing x form a local basis at x. Oh, okay. And then he makes a little claim. A topology can be described by listing the neighborhoods of its points. And this is an exercise. So now we've got another character. We could build a topology by giving a basis. We could build a topology by just listing the open sets, the basic thing we did. We could build a topology by listing all the closed sets for the set. We could build a topology by listing all the neighborhoods. These are equivalent ways of capturing what a topology is. And all of these were competing for like the primary definition of topology and the invention of this stuff, right? So I think there may be one or two more other ways. Like if I wish you guys could talk to Dr. Bavinga. He's a topologist, right? So he knows. Anyway,
Should bring him in for a few lectures.
bring him in. Yeah, I had to go through the guest lecturer.
Wait, where's he from?
What's that?
Where's Dr. Davenka from?
Oh, Dr. Mavinga? He's he lives over that way. Over there a bit. He's still around though. He's adjuncting at Longwood and
Oh.
CVCC. And maybe we can get coffee with him sometime. I don't know. Let's see here. He gave me some really nice coffee for Christmas. Where is my? Oh yes, the juice. All right, now, finally, we have come back to the theorem with the mysterious notation from last time, which hopefully will be less mysterious now. All right? And it is absolutely a beautiful, beautiful thing that he has written here. I really, really like how this leads up to this. It sold me on his notation and his terminology. Lemma 3.25. He says if f, now we're back into the continuous maps section, okay guys? So if f is a mapping from x to y, all right, x and y being topological spaces, then f is continuous. All right, f is continuous if and only if f of a closure is a subset of the closure of the image of A. And that has to be true for any subset of the domain. Was that me?
I think so.
Was that one of you guys?
Sound like a computer.
Yeah. I didn't even think it. At least from my side.
I told you guys I had this problem with my computer not really turning off.